let's change the position of the switch to the second one. What happened there? Then, if we turn off the switch 1, the voltage drop on the capacitor will be equal the maximum value, E. That's right? I think yes. Okay. If we turn on the switch to the second position, then we'll observe that the current will be passing through in opposite direction. Then was opposite direction when we have the charging phase. Why? Because we make the short circuit, in fact, in this case, and the top plate of the capacitance has the higher potential. So, of course, the current should passing through from the positive to the negative. We can say that at this moment in the discharging process, the capacitor, it is like the voltage source for us. Yeah. Of course, it is not the voltage source, but it looks like the voltage source with some capacitance. Great. So we have observed the changing of the current direction. That's why you take a look at the bottom graphs. You can see that the discharging process gave us a negative peak for time equal 5 tau, for example. And this peak is negative to the value equal E over R. Yeah, that's right. This is the maximum value. And this is going to 0. So as you see, the charging and discharging process in the RC networks produced the current peaks, as you see here. It is very, very dangerous according to the noise system, in fact, or noise electronic circuits. You have to remember, anytime when you have the electronic circuits, which is consists of capacitors, we can expect the peaks, in fact, of the currents, especially if we have some switching elements. Yeah, for example, I don't know, DC-DC converters, for example. Yeah, that's right. So there, so we have to use, in fact, that in that circuits, some filters, yeah, to reduce these peaks. This is very important. Okay, so what about the the voltage drop on the capacitor in this case? When the capacitor was full, I mean they collect the maximum charge, they have the maximum voltage drop equal E. When we put the position of the switch to the second one, we'll observe what? The decreasing of the voltage drop on this capacitor. Why? Because the charge from the top is going to the bottom. In fact, not the charge positive is going, but the negative one, in fact, is going to the positive one. Yeah. However, we are consider the current like the opposite to the electrons movement. Okay, so that looks like the charging and discharging process for the RC network. However, one thing is more important. Sometimes the discharging phase is considered for the different tau constants. Why? Because if I will put it here, the extra resistance, in fact, the discharging process will be considered for the different tau value. The tau value here will be how many? If I will put it here, the resistances, it will be the series connections between this resistor and this extra one. So the tau will be equal C multiplied by R plus the second resistances. Okay, I think, sorry. Yeah, I will talk about it a little bit later. At this moment, let's consider what happened when our capacitor wasn't empty when we initial the charging or discharging process. In fact, we are starting not from the zero, but from some initial value, yeah, some voltage drop what was previously on this capacitor. What is so important for you? You have to just remember the universal equation for the transient analysis, for transient response for the capacitor. It looks like that. Vf, it is the final value. Vi, it is initial, and that's all. So please just remember it, this equation. This is for the charging for the charging phase. If we have the initial condition, please take a look at the situation when the initial value will be equal 0. Yeah, for example. So if you put the initial value by 0, as you see, everything will be correct. So that's why it is the universal one, universal equation. Please remember it. Okay. What else? Of course, if we have the voltage drop on the capacitor, we can also, for example, finding the time, just changing this equation and trying to calculating the, for example, t. Yeah, of course, because we've got the exponential function here, we have to use the function like the logarithmic with the base of e. This is just the mathematical one, mathematic problems here, but only that. What else? Let's just consider some example with the charging and discharging process, how we can calculate it. So please take a look at this picture. Okay, I forgot about something. Yeah, that will be better. Okay, yeah. So first of all, if you wanted to draw how it looks like the voltage drop on this capacitor during this discharging and charging process, first of all, we have to find the mathematical expression for the first phase, yeah, for the time equal 0 when the switch is turned on to the first position. So if the capacitor was empty, yeah, so first of all, let's calculating the tau, time constants. As you see, this is just the resistor R1 connected directly to our capacitor. So it is very simple to find the tau. It is R1 multiplied by C. As you see, if I put our values here, we'll get the 1 milliseconds of time. Great. At this moment, we know how the function of the voltage drop on this capacitor looks like in the charging process. The maximum value is E, and we have to take equations like the 1 minus E to minus T over tau. So if the E is 12 volts, we have to just substitute the values, and we've got the simple equation for the VC. What about the current? Current is going when you turn on the switch to the first position, we know that the current has the maximum value and then are going to 0. So the maximum value is limited by this resistor. Yeah, that's right. And the maximum value it is equal E over R1, and this is it. And this is the expression for the exponential function. The tau is the same, 1 milliseconds, yeah, because this is just the R1 connected directly to the C. Okay, so it is equal 0.6 milliamps multiplied by E to minus T over 1 milliseconds. That's the expression for the voltage and the current in this branch. What else? What happened when after time equal, for example, 10 milliseconds? What does it mean 10 milliseconds? If we know what was the time constants for the first case, it is equal 1 milliseconds, so we can say that the 10 milliseconds, it is the time equals 10 times of tau. Yeah. Okay. So after this 10 tau time, we change position of the switch to the second one. As you see, the second one, it is the position when the capacitor and this resistor remain in the open circuit. What happened then? This 10 tau means this is the higher than 5 tau. Yeah? So we can say that when we turn on the switch to the second position, we've got the steady state. Yeah? So because we are considering the capacitor like the ideal component, the liquid resistance inside the capacitor is equal how many? Infinitive. Yeah. So there is no liquid current here. So when the switch is turned on to the second position, in fact, the voltage drop on the capacitor stay the same. What about the current? There's no current flow here because we've got the open circuit. So that's why the VC is still 12 volts and the current is equal 0 amps. In the next step, we change the position from the second to the third one. And what we've got? We've got the situation that this switch is connected with 3 terminal. In fact, we've got the closed loop. Okay, so something was happened here. First thing is that we've got 2 resistances which are connected in series. What does it mean? If you wanted to find the time constants for discharging process, it will be named like the tau prim, for example, and this is equal at general RC. In our case, the R, it is the series connections of the R2 and R1. So that's why we've got the R1 plus R2 multiplied by C. C stay the same, of course, and then we've got finally 1.5 milliseconds of tau. Great. What about the VC? We know that the discharging process is given by formula like that. The initial value, it is VC, and we know that from the previous steps, the initial value, it is 12 volts. That's right. The maximum voltage drop was the 12 volts. So that is the initial one value here, and the expression for exponential function, which is going from the maximum to the 0 for discharging process. That we can describe it. Great. So we have to just substitute by E 12 volts, and the time constants here, it is the time constants for the discharging process. So it is minus T over 1.5 milliseconds here. So as you see, we change the time constants. What about the current? Because if the switch is connected to the 3 terminal, the current will be passing through the opposite way that was described previously. Why? Because this is the higher potential, this is the minus here, so the current is going from plus to minus. So that's why we have the minus here. The maximum value is starting from voltage, maximum voltage, which is limited by the resistances in our closed loop. As you see, this is the serial connection of the 2 resistances. That's why it is E over R plus R2 in this case. And we have to just substitute by T prim value of 1.5 milliseconds. If we are calculating it, we'll get the current equal minus 0.4 milliamps multiply our exponential function. How it looks like on the graph, it is rather simple. The first phase was from the 0 to 10 milliseconds. Yeah, 10 milliseconds. It is given for the 10 tau for the first step. So we've got the increase in the voltage drop on the capacitor. Here after 5 tau we've got the steady state.
Tak.
And for the next 5 tau time, we switch off for changing the position our switch to the third one, and we starting or initial we make the initialization of the discharging process. But here the 5 tau, where we can observe the steady state, it is different because for discharging process we've got a different tau constants value. Okay, what about the current? At the beginning, the current was starting from the 0.6 milliamps and is going according to the exponential function. After 5 tau is reached the zero almost. Yeah? So we've got the steady state, and suddenly at the time equal 10 milliseconds, we turn on the switch to the last position, and the current direction was changed. So that's why I can observe the peak, which is going down to minus 0.4 milliamps, and then this discharging process is going to zero. Also here, we've got the different tau constants. Okay, I think it is, at this first look, maybe it looks like so strange, yeah, but I think at this moment you understand very well. Okay, we can also describe the another expression for the current which is passing through by the capacitor, and we can use here the derivative function. Why? Because as you see, for the DC conditions, for DC value, when we have the steady state, you can see that the current which is passing through by the loop where we have the capacitor is zero. Yeah? The voltage drop on the capacitor also has a steady state, and it is fixed. It is maximum value. Where we can observe the changing of the current, when we have what? When we have some situation where we're changing, when we changing something in our electronic circuits. For example, we use some switch, we change it. When we have any changes, produce the changes of the current and the voltage on the capacitor. That's the very important. So as you see, that's why for the expression for the IC, we'll have the derivative of VC according to the time. What does it mean? The current of the capacitor current depends on changing of the voltage on it in time domain. Of course, the value of the current depends on the capacitance. Yeah, of course. If we have the higher capacitance, which means the higher charges can be collected on the plates, so it is possible that the current also will be higher when we, for example, turn on the switch and we observe the current which will be passing through by the circuit. Why? Because the capacitance is so huge, lots of charges wanted to go from the bottom plate to the top one. So if we have the more charges, we can observe the more or higher current, in fact. Yeah. So please just remember this equation, and please remember that the current depends on the changing of the voltage on this capacitor. That's why for the steady state, anytime we have the changing of the voltage is zero. So as you see, the current also, if we just substitute by the derivative of VC to dt is equal zero. So C multiplied by zero gave us the zero. Yeah. Okay. Okay. Next thing, the capacitors can be connected together in the series way and the parallel also. What happened when we have the parallel connections of the capacitance? If we consider the charges which is collected in any capacitor in the parallel connections, we can summing up the charges. What does it mean? If we because we know at this moment that the charge Q is equal C multiplied by V, yeah? So the total charges in the parallel connection, it is given by the total capacitance multiplied by V. V, it is E, in fact. It is equal the capacitance for any capacitor multiplied by V1. Because the V1, V2, V3 are the same like the E, we can say that the total capacitance is equal sum of the capacitance of the capacitance of the capacitors which are connected in parallel. So that's the reason why for the parallel connections of the capacitors we have to just summing up the capacitors. If we have the capacitors which are connected in series, the total charge are the same for anyone, the capacitors. So that's why we can say that the total capacitance for the series connections, it is equal, the reciprocal of the total is equal sum of the, this is the sum of the reciprocal of the each capacitance. How we can, very easy to remember these equations? Very simple. You have to just remember what the total resistances connections for parallel series ones and for capacitor is opposite to the resistances. Just only that you have to remember. For the capacitor, for the capacitance, we've got opposite equations according to the resistances. And for the inductors, we've got the same like for resistances also. So only that information is needed, and you have to don't remember, in fact, these examples. You have to just remember only the resistance, the total resistances for the parallel series connections, and just remember that for capacitive, they are opposite. That's all. Okay, what about the energy which is stored by the capacitor? If I will ask you, for example, what is the dissipated power or energy on the capacitor, and you tell me that, oh, it is, for example, 1 watt and something, never mind how many, then I will tell you that it is not true. Why? Because the energy, it is directly connected with the power, yeah, of course, yeah. And let's take a look, what is the power when we have the charging or discharging process according to the capacitor. The power, we know that is the what? Voltage multiplied by current. Yeah. So we've got the power on the capacitor is given by formula VC multiplied by IC. However, when we have the, for example, charging process, the current looks like that. That's the function of the current. That's the function of the voltages on this capacitor. So how it looks like the function of the power? It looks like that. This is the blue one's function. They have the maximum point where these two functions are crossed, round of course. But for the steady state, as you see, the power is going down to 0. So we can, if the power is equal 0, so we can say that there is the dissipating power on this component. That's why you have to remember that the capacitor, they haven't any dissipating power or energy. Only we can say that we have some power or energy which can be stored by the capacitor. What is the matter of this energy? What is the what is the medium where this energy is stored? The medium, it is the electric field between the surfaces. There is, in fact, our energy which can be stored in our capacitance. Great. What this energy can be presented by some formula. It is given here. Um, of course, the E, it is the voltage on the capacitor. That's why it is the 1 over 2 CV squared. Okay, if you wanted to go farther and we replace the V by Q over C, so you can see that it is possible to find the energy stored in capacitor having only the Q and the capacitor. This is Q squared over 2C. Okay. Okay, so I think it is good time to go into the next component. It is inductors. Okay, so it is the similar for the electric fields for the charging. The magnetic field is connected with the magnets. Yeah. Okay, so we've got some materials which has some magnetic domains. These magnetic domains are very low, of course, and they have the two poles, yeah, north and south. Yeah, this is the typical. This is the magnet. Yeah. What is so important here? Where's the differences between the charges and this magnetic or magnet poles? You know that I told you that the one pure charge produces the electric field, which is radiate around the space. Yeah, that's right. So we can say that the magnetic field or electric field or electric flux line has the initial point. They have source. This source is given by the charge. The charge produces the electric field. Great. What about the magnetic field? Here is we have the problem here because we can say that the magnetic field haven't got any ending point. Why? Because if you have the magnetic domain, which are constructed like the Sn, 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 and are connected together, and you know if we broken the magnet, so we'll have another two magnets where we'll have the south and north pole, and again south and north pole. So that's the reason that we can say where is the beginning of the magnetic field, where it's starting. So that's why we can say that the magnetic flux line are built by the continuous loops. Okay, we haven't find in fact the place where the magnetic field has source. Okay, we know that the flux line of the magnetic field goes from north to the south pole, and also we can determine the density of the flux lines according to the magnetic field. Yeah, if we take it some areas B and A, we can say where we've got the higher density of the magnetic field and where it is lower one. Okay. And again, of course, I know that you know about it about the magnets. That information that we have the two magnets and these two poles are different. So the two magnets will be will observe the force of attractions. Of course, yeah. Why? Because the north is connected to the south south pole. And we know that the magnetic flux line is going from north to south. So as you see, that looks like the magnetic flux line. And what happened? What happened here on the end of the second magnet? Of course, we know that the magnetic field, as I tell you, they makes creating the closed loops. So from the north should going back to the south. The first one. What about when we have the two magnets and they are connected together with the same pulses? Of course, there's the repelling force here. Why? Because magnetic flux lines looks like that, going from north to south. Yeah. Okay. What else? We can change the direction of the magnetic flux lines. we can put or force to passing through the magnetic flux line through some length, through some different shape, using the ferromagnetic materials. For example, the soft iron. I can say that the ferromagnetic materials, it is like the wires for the current. Yeah? We know that the current is passing through by the wires. Yeah, for example, copper wires. And the same story is for the ferromagnetic materials. This is like the wires for the magnetic flux line. That's why we can change the shape of the flux lines using the ferromagnetic spheres. If we take it, for example, glass, yeah, which is not the ferromagnetic material, we will not observe any changes in the flux lines directions. Okay, that's a very important information. Great. What else? I think everybody knows that the magnetic field is produced due to the current current flow. Yeah? So if you have the just straight wire and we observe the current flow, the magnetic flux line will appear around this wire. Sorry. Sorry. Okay, that's better. According to the right-hand rule, how it looks like, I think you know this rule based on your basic school, I think. And what happened when we make the turn by the wire? How it looks like the magnetic flux line in this case? It looks like that. If we make more the turns, we can produce something which is called like the coil, which is named like the coil. So we can say that the current which is passing through by the coil produce, in fact, the magnetic flux lines, and according to the bless you. Okay. I'm just take a look at the chart. Using the right-hand rule, in fact, we can determine what is the direction of the magnetic flux line, where we can create flow. Of course, I told you that ferromagnetic material create, in fact, the way for the magnetic flux line. So what we can do here, if we put the steel, so it is the ferromagnetic material, inside the coil in this case, so in fact more produced magnetic flux lines produced by the coils will be passing through by the steel core. Yeah. So in fact we can build in that very simple way the electromagnet. Yeah. And the strength of the electromagnet here is higher than just the air coil. Why? Because we force to passing through the magnetic flux line through these ferromagnetic materials, which means that here and here we have the higher density of the magnetic flux lines. So the strength of the magnetic field is higher here and here. Yeah? Okay. It is similar for the capacitor, where we put inside the plates the electric materials. We can increase the capacitance. Yeah, here we can increase the magnetic field strength. In fact, using this material also. Okay. So as you see, the flux density, which is named B, it is the formula given by the Nikola Tesla. It is equal. The magnetic flux lines, magnetic flux over the area. Yeah, that's the density. Okay. What about the electromagnets? What is the force, electromotive? It is named like the magnetomotive force produced by the electromagnets. You have to know that it is proportional directly to the number of coils. Why? It is simple, because any rounds produced more magnetic field. It is simple. And also we know that the magnetic field is produced by the current. If the current is going up, the higher magnetic field is produced. That's why the magnetomotive force, it is depends on the number of turns, yeah, and the current value. Great. Very similar to the capacitance. Also, as I said, we've got some materials. We have some special properties according to the magnetic field. These materials, any materials, in fact, has some permeability. The permeability, it is the same like the permeability. It is the same like the no. I forgot it in English. Like the E in the for the capacitor for the electric materials. This permeability also is given according to some reference. For this case, the reference, it is the air. Yeah, of course. In the Europe, you can say that this is the permeability of vacuum. However, it is the same. So the relative permeability μ r is given by the μ over μ zero. μ zero, it is the permeability of air. So if the relative permeability of material is higher, it means this material this material is better for example, how can I say it? That materials is like the inductor for the magnetic field. Yeah. Okay. Whoa, what is it? What else? We've got the three types of materials. What are you doing with this? What is the? Oh, nice heart. It is for me. This red heart. Well, very nice. I like it. Okay, so I think you are a little bit boring, yeah. Maybe. So we've got the three types of materials according to the magnetic fields. There are the ferromagnetic material, paramagnetic, and diamagnetic. Everything what you have to remember here, it is what the relative permeability are connected with this three type of materials. You have to remember that ferromagnetic materials has the μ r higher than 100. But much more than one, much more. For example, 3,000, 6,000, for example. It means that the ferromagnetic materials, it is good wires for the magnetic fields. It is like, for example, nickel, iron, steel, cobalt, a lot of alloys, and something like that. Paramagnetic material, it is the material where the relative permeability is a little bit higher than one. Yeah, so they have some properties of ferromagnetic, but these properties are so weak. And this is the, for example, sodium, nitric oxide, platinum, oxygen. Yeah. And diamagnetics. Diamagnetic materials has the MER lower than 1. So that's why, just for example, glass. Yeah, that's why, in fact, they can be used to change the direction of the magnetic flux line. In fact, there is no influence for magnetic flux lines where it is crossing through copper, aluminum, wood, glass, and also the air. So please remember this these values. It is important. Okay, this the permeability of the material is commonly used for a lots of electronic devices like the transformer, generator, and the sound speaker, for example. Also, without this material, we'll have the transformers. Why? Because as you see, this is the typical transformer. Yeah? We have the primary coil and the secondary, and they are connected together by some laminated sheet of steel. Steel, it is the ferromagnetic material. That's why the magnetic flux line, they are not going outside, but they are leading inside the ferromagnetic material. What does it mean? It means that almost the whole magnetic flux lines are passing through by secondary coil. Yeah, so it means that do you know what is the I forget what is the sprawność in English? Efficiency?
Yeah, I think so.
Yes.
Yeah. Okay, thank you. So as you see, the efficiency for the transformer, then it is so huge when you use the ferromagnetic materials for to leading the magnetic flux line. The same story it is for the loudspeaker and for the generator, as you see. Yeah. All right. What is so important here? The ferromagnetic materials has some saturations. What does it mean? It means that they have leading very well the flux lines or magnetic field. However, there is some point where the magnetic field is so huge, then in fact can we observe that that this material can stop leading this magnetic field so good. You can say that the core is saturated, or the ferromagnetic is saturated. What does it mean? It means that that if you produce so huge magnetic field strength in the primary coil, and we'll have the saturation of the core, in fact, on the secondary, we can observe the increasing of the voltage then because the core is saturated, in fact. Yeah. Okay, that's the one thing what is important about the about the ferromagnetic core which is used in electronics. Okay, what about the inductance? The inductance is given by that formulas for the typical coil. As you see, we've got some rounds here. We've got the core, the ferromagnetic core. We've got the end turns. We've got some area of the sorry, of the core. So the L, the inductance, it is equal the permeability multiplied by n squared, the square of number of turns, multiplied by area over the L. L, it is the distance here. In the next semester, I think you have some course where you will be able to find, in fact, this expression for inductance. You can solve some expressions and get that equation also. But at this moment, it is not important. You have to remember only that the inductance has the unit is Henry, and that's all. That's all. Sorry. And also the same story. Like for the capacitor, if you have the two inductors, one of them it is the inductor with the air core, and the second one it is the the core created by some ferromagnetic core with the μr value. The relative permeability is so huge. The final inductance for the coil with ferromagnetic core, it is μr higher than the inductance for the air core coil. What about the equivalent model for inductors? Yeah, it is the same story like for the capacitor. We have to remember that, of course, we've got the pure coil. Yeah, it is the ideal component. However, we have to know that the coil are made from the, for example, the copper wire. We know that the copper has some resistances. Yeah, so if we make much more turns of the coil, we'll get the higher resistance of the wire, in fact. So this RL will be much more higher. What is the stray capacitance here? We know that if we wanted to create, for example, the turns, yeah, these turns are touched together. That's right. Yeah. So if the wires are not isolated, in fact, our coil will be not working because, as you see, for example, here and here, the wires are touching together. So in fact, we'll be having any turns, but the short circuit. So we haven't the inductor. So you have to know that the wires should be isolated through a very thin film of the insulator. Okay, it's true. So if we consider the two turns, we've got what? We've got the first turn and second one, and between them it is the electric materials. So, in fact, we can say that between them we've got some very low, but there exists some capacitance. So this capacitance it is between any turns. So we name it like the stray capacitance here. Yeah, this is this component. However, it is so low capacitance. That's why in fact in the model, in practical equivalent model for an inductor, we are leaving this stray capacitance and we just replace by the pure the inductor can be replaced by the equivalent model only, which is consists only the RL and the L, and that's all. The next thing, sorry, we know that if you have some conductors, if you have some coil which is given inside the magnetic field, it is possible to produce some induced voltage across the coil. Yeah, this is the Faraday law for electromagnetic inductions. How it works? You have to know, according to the Faraday's law, that the induced voltage across the coil inside the magnetic field, or according to the magnetic field, is given by that formula. It is directly proportional to the number of turns, yeah, and the changing of the magnetic flux in time domain, which is passing through by our coil. What is so important? The changing of magnetic flux should be, or because the magnetic flux should be passing through in right angles to the magnetic field. So that's why to observe the induction of voltages, in this case, we have to move our coil from top to bottom and so on, like that one. Will not observe any changes, any induced voltages, if this coil will be moved in that way. Yeah? Also, in this case, the conductor should move in that direction, so it is the right angle to the magnetic flux, not in that direction. Okay, that's the that we can observe the induced of the voltage across the coil in magnetic field. The next thing, I think you have to just reading more about the Lenz's law. What is the Lenz's law? Very briefly, the Lenz's law told you that if we have some induced effect in the coil due to changing the magnetic flux, this induced effect has the opposite, or the way of the induced effect is opposite to the cause that produces it. You have to, for example, feel it, in fact, how it works. That's why I'm just want you to read about more about Lenz's law. Why? Because at this moment I not be able to show you, in fact, because I in fact need the board, whiteboard, and just show you how it works. So I'm just limited at this moment. Because we have to use it here, the right hand rule, to determine the current, for example, direction, which is passing through in the coil due to, for example, changing the position of this magnet, and what is direction of induced B field. So maybe please remember me if you're coming back to the university. I think it will be a good opportunity to show you how it works. But at this moment, believe me, it is very hard to show you how it works, having the possibility to direct interaction between us and having the whiteboard. So the next thing, we know that the current which is passing through by the wire produce the magnetic flux lines or magnetic fields. However, in the other way, we know that we've got the magnetic induction process when we can observe the changing of position or changing of the magnetic flux line which is passing through by the coil. So we've got the two different effects here. So if we have the current which is passing through by the coil, we know that we can produce the magnetic field around this coil. And we know also that if we have the magnetic field around the coil, and this magnetic field, according to this law, the Faraday law, depends on the changing of magnetic flux. As you see, if you have in the changing of magnetic flux, we have in the induced voltages. It is equal to 0 if you have in the changes of magnetic flux. So it is possible to induce on the terminals for the coil some induced voltages. And we know due to the the Lenz's law, that this voltage, induced voltage across the coil, has the opposite way to cause it. Um, so we can say, and this effect is named like the choke effect for the inductor, for the coil. How it works. Also, it is very hard to show it at this moment. However, I'm tried. If we'll have the constant current which is passing through by the coil, they produced the stable, the fixed magnetic field around the coil. So according to the Faraday's law, there is no changing of magnetic flux which is passing through by the coil, yeah, because the magnetic flux is stable, is fixed. Okay, so we don't produce any voltage which is induced across the coil. What happens when the current will be increasing and passing through by the coil? So the current, when it is increasing, we know that the magnetic flux or magnetic field also will be increased. Yeah. However, if the magnetic flux increased, which is generated by the coil, the same magnetic flux are changing because they are increased. And this magnetic flux also passing through by the coil again. And now we can produce some induced voltage across the coil. What will be the direction of it? It depends on the current direction and the magnetic flux line directions. We know that we will induce the magnetic flux lines, magnetic flux line or magnetic field opposite to the magnetic flux changes according to the current flow. That's why we can observe that induced voltages will have the positive potential here and negative here according to the current direction when it is going up, for example. What does it mean? If we'll observe, for example, the changing of the current, yeah, and we'll have the induced voltages across the coil, it means that this current, which is increased, in fact, will produce the voltages across the coil, which wanted to decrease this current which is passing through by it. So that's the choke effect. What does it mean? If the current are decreasing, in fact, the coil make it that the current is limited, in fact. They wanted to go up. However, due to the induced voltages across the coil, this current is stopped a little bit. Yeah. How is so let's go to the transient analysis for the inductors network, RL network. What happened for in this case when we turn on and turn off the switch? Okay. What happened the first moment? Let's consider the current which is passing through by the coil. Okay, let's turn on the switch. At the first, sorry for that. One more thing. Of course, when this circuit is opened, we've got just the pure coil. We haven't any voltage drop on this on this coil. Yeah, of course, this is simple. Now we turn on the switch, and for the first moment, we can observe what? We can observe the situation that the coil, it is made by the wires. So the resistance of the coil is very, very small. So we can say for the ideal inductor, we can say that they have the zero of resistances. So at the first moment, the current IL wanted to go or passing through by whole components, and it is only limited by the resistances. Yeah? The ideal coil has the zero of resistances. So in fact, at the first look, the current IL should have the value E over R. Yeah? However, it is not true. Why? Because at the first moment, as you see, the current is starting from zero. Question is why? Why? Because we've got the choke effect. We've got the choke effect. We've got the voltage induction across the coil. Why? Because at the first moment, we make the situation that the current from the state equals 0 amperes suddenly is going to the maximal one, IL. So we've got the huge, very speedy changing of the current. As you know, look, the VL voltage drop on the coil due to the Faraday's law, yeah, depends on the changing of the current in the time domain. If these changing are so huge, then we've got the huge voltage induced across the coil. Okay, so as you see, the changing from 0 to the maximal one, it is the one of the so fast changing of the current. So due to the choke effect or Faraday law, we can observe the induced across the coil the VL value. Great. So if it's true, that means at the first moment, this potential of this point will be the same like the E, which means at the first moment, we have the zero current flow through the coil due to the choke effect. What happens next? The changing of the current are slowing down. So the voltage induced across the coil also decreased. So it is true the current is going up. Yeah, it's going up, and the after 5 tau, it's given the maximum value. Maximum value given for the 5 tau, I mean it is the steady state. It means that there is no steady state. It means that the current is stopped. The current are not changing. So we haven't the induction of the voltage across the coil. So this voltage is equal to 0. There's no changes. There is no induction voltages. So in our electronic circuits for the steady states, we can consider only the resistances here, R. So the currents, it is given by the formula E over R. That's the maximum current here for the steady state. All right. So what is the expression of, sorry, I forgot about it. Also for the RL transient analysis, according to the RC analysis, the charging or discharging processes or storage phase or discharge phase for the inductors are described for the same exponential functions. So what is the current IL for the storage phase? Here is given by the maximum value. It is the E over R, that is maximum current, and this is 1 over E to minus T over tau. Where's the differences here? Because this is the RL network, the tau, it is given by the different formula. It is the L over R. So we have to remember it. Please remember it. Tau, it is L over R. For the RC networks, as you remember, tau, it is equal R multiplied by C. For inductors, it is the L inductance over the resistances. Great. What about the voltages, which is across the, which is produced on the coil, across the coil? Of course, this is given by that formula E. It is equal minus T over tau. The maximum value, it is here. This is the power supply value, and is going down, yeah, because due to the Faraday's law, the induced voltages are decreasing because the currents changing are so slow, yeah. And for the after 5 tau, the change of the current is equal 0. So in fact, the voltage induced on the coil also have to be 0. Great. Sorry. What else? So we can say that if we consider the storage phase according to the transient analysis for RL network, for the first moment you can say that the inductor it is the like the short circuit. Yeah, we could replace it like a short circuit at the first moment. Yeah. What else? Sorry. No. Please don't remember the last sentence. The short circuit. It is the equivalent, for example, the model for the capacitor when we have the for the coil when we have the steady state, of course. Yeah. If we have a steady state, then we can say that we haven't any voltage drop on the coil because they have the resistance equal 0 for the ideal component, and then we've got the maximum current here, which is passing through by these components. Okay, and the same story about the initial conditions. Also, it is possible that the coil have some initial current. It is possible. So I want just to remember the formula for the current passing through by the inductor for the initial conditions. As you see, it is the same like previously. Also here we've got the final and initial value. So in fact, this is not the changing. The changes is, there is no changes here. You have to just remember. For the capacitor, we've got the voltages here, and for inductor, we've got the currents. Okay. What about the release phase? So what happened when the switch is open? We will have the storage phase. Yeah, we turn on the switch, and suddenly we wanted to switch off. What happened? This is very interesting because if we have the steady state and this switch is stay closed, we know that we've got the maximum current which is passing through it because the coil in fact hasn't any voltage drop on it. Yeah, because this is steady state. The current is given by formula E over ER. If we for some time we turn off the switch, suddenly we will observe that the maximum current are stopped flowing. So according to the inductor, we can observe dramatically drop the value of the current. So according to the Faraday's law, we've got very rapid change of the current. Yeah. However, the direction of the changes is opposite because the current are decreasing to 0, not going up, but decreasing. So we can observe in the coil, in fact, what? The induced of magnetic field, or magnetic field, of course, but according to the shock effect, we observe the induced of the voltage across the L. However, the direction of it will be opposite to the according to the storage phase. Why? Because for the storage phase, we observe the increasing of the current, but for the release phase, we observe the decreasing of the current. So, as you see, we'll observe the induced of the VL across the coil in that polarity. Okay, this switch is turned on, but the induced voltages is directly connected in series, because this is the open circuit at this moment. It is directly connected in series with the voltage source. So as you see, we've got a positive potential here, negative, positive, negative. Look, we'll observe on the contact terminals the positive potential here, but negative here. And the contact voltage across it will be equal the sum, according to the Kirchhoff voltage law, the sum of the E plus VL. What does it mean? In release phase, in fact, we can observe the higher voltages in open loop, higher than the input voltage. What does it mean? We can observe here the sparks, in fact. Why? Because we've got the huge voltages between the two terminals on this, or two position of the switch, metal contact of the switch. When we wanted to opening, yeah, the distance between these two metal contacts is rather low. What does it mean? We've got the contact is in the air. Yeah, we've got the air conditions. We know that it is possible to observe the sparks in the air. Yeah, when we will have we will have the so huge voltage across these two, the point, for example, the sparks is, can be observed. So you can say that is the ionization effect of the air. Yeah, we can say that the ionization of the air depends on humidity, depends on the temperature. However, it is around 30 kilovolts per centimeter. If you have the two, for example, metal balls, and we'll have this metal balls will have some distance in the air between them, and we plug in the 30 kilovolts between these two balls, metal balls, and the distance between them will be in the air, of course, 1 centimeter. Then we can observe the current flow through the air. It is like the light storm. Yeah, this is the same story. Also, the sparks, which is observed here, also this is like the light storm, in fact. However, when we are opening the switch, for the first moment, the distance between them, it is so low, so small. So if you have for the air 30 kilovolts per centimeters, and there it is some micrometers, as you see, in fact, we'll have a lots of voltage connected across the connectors to get the sparks effect. Yeah. Okay, so that's the reason why at home, when you turn off the switch, sometimes you can observe that in your connector, in your I don't know how it's in English at this moment. I can remember it. The contact. Do you remember the switch? Yeah, can be switch. We can name it the switch. Yeah.
Yes.
Of course.
Or do you mean the power plug?
Yeah, the power plug.
Yeah, okay.
Yeah. No, the power plug. If you turn off, yeah, sometimes you can observe, yeah, some sparks inside there. Yeah. Why? Because your power network, in fact, which is hidden in the wall and in the wall. In fact, there is a lots of wires, and also they have some inductance. Yeah. Okay. So the currents are passing through by this the power lines. Yeah. So if we take it together, everything that we've got the current, and sometimes it is huge current, a few amperes, for example. We know that we've got some network of the power lines which are giving us some nice inductance. That's why we can observe the sparks in the switches, on the switches. but when we turn off it. Yeah. Sometimes it is possible to observe the sparks when we turn on the switch. However, it is just possible, it is more visible. Why? Because at the first moment we are limited to the voltages, to the voltage which is delivered by the power of the network. So we haven't observed here the increase or induce some extra voltages across the contact. So the very, very low, very small sparks can be observed when we turn on the switch, but they are connected directly to the current flow for the voltages, which is equal just E, yeah, the initial value of E, and the distances between the contacts should be so small to make the ionization of the air. That's why it is so. It is not very often observed, but the spark effect when we have the release phase, when we turn off the switch, it is really observed because we have the higher voltages which is generated, or which is induced in our network, and this is higher than our initial voltage source. Okay. Well, so that's the story about the release phase and the sparks. I think it is rather interesting, yeah, what happened with the coil one, why we have the sparks. Okay, what else? For example, if we have that situation, that circuit, as you see on the bottom of the screen, first of all, we have to initial the, for example, storage phase when we closed this switch. What happened there? We know that the first moment the current will be equal 0 is going up, and then we can observe that the voltage across on the VL is going from the maximum value to the 0, and then after for the steady state, in fact, the current IL is going to the maximum value. Yeah, that's right. And what we have here at the first moment, we can say that it is the short circuit. The inductor, it is like the like the open circuit, and we generate the VL, the maximum value. What happened when we open the circuit here? When we open the circuit, we'll observe the situation that the current direction will be the same. We'll have the same direction here. If it is true, it means the changing of the current produced the VL voltage according to that equation. So we'll observe, in fact, the changing of polarity by our two resistances. Here we'll have the positive and here we'll have the negative. Why? Because the current are decreasing. So if we turn off this switch, so that's why we'll have the minus VL, and VL, because this is the closed loop, should be equal according to the Kirchhoff voltage law, yeah, because this is a closed loop, should be equal the same like the sum of the voltage drop on each components here, because this is just the resistances. Okay, so when the switch is opened, we can say that make these calculations, yeah, we can get that this is defined by that formula. At this moment, it's not very important. However, I'm just wanted to show you what is the release phase, how it looks like, and how we can find the expression for the VL for this case. What else? What about the the currents. So the currents, and again, when we have this changing process, you have to remember that they wanted to go from the maximum to the zero. Yeah, that's right. Yeah, because in the storage phase, this current IL, it was maximal, and for discharging for the release phase, sorry, this current is going from maximal to zero. Yeah, so that's why we can observe the changing of, of we can observing the induce of the VL across the coil, and the current can are starting to flowing in the closed loop. This current IL, as you see, it is given by that formula. And this moment we can use this universal formula, because we know that in the closed loop, for some steady state, we'll observe that the final current will be equal zero. Yeah, because in fact we haven't the any voltage or current source here. Yeah, for the steady state. So if initial current is equal to 0 amperes, so if we just plug in, so no, not the plug in, but replace the IF by zeros, so we'll have the current IL is given by that formula, the initial value multiplied by E2 minus E2 tau prime. Tau prime, it is very important here, because for a release phase in this situation, we have the two resistances which are connected in series, so you have to remember to summing up these two resistances, creating the total resistance, and put it to the equation for the tau expression. Okay, so what next? Also, we can we can describe the mathematical expression for the voltage across the resistances also using the just the Ohm law. Yeah, why? Because this current IL also passing through by this resistor R1. So if we find the IL, this very simple to determine using the Ohm law, what will be the voltage and voltage drop value, yeah, on these components. Yeah, just by IL we have to just determine this formula. And as you see, the R1 will be reduced, and here it is the E to E2 minus T2 over the tau prime. Also the same story it is for the VR2. And the next thing, how we can connect the inductors in parallel and the series. Everything what you have to remember, for inductors, in fact, it is the same. The total inductance for the parallel on the series connection, it is the same like for the resistances. So if the inductors are connected in series, we have to just summing up the inductance. Each are connected in parallel. The reciprocal of the total inductance is equal to sum of the reciprocal of the each inductances. And also, like for the resistance, if we have just two inductors connected in parallel, we can use this formula like for the resistances. Yeah, in the numerator we've got the multiplication of the inductance, and the denominator we have to just summing up these two inductance. Okay, so this is a very simple example how we can consider the electronic circuits for steady state, which it consists the coil, for example. So as you see, this is the very simple electronic circuits. We've got some two coils, some resistances, and the question is, how it looks like our electronic circuits after time equal 5 tau. I mean, after steady state. We know that if we had the storage phase for inductor at the beginning, we observed the inductance of the voltages on this component, yeah, and if the time goes by, the voltage is going down because the currents are decreased, so the changing of the currents was so slowly. And finally, after 5 tau, we can say that we've got a steady state. There is no current changes passing through by the coil, so there is no voltage induced across the coil. So we can say that for the steady state, the coil, it is like the short circuit, yeah, because for the ideal, they have the zero of resistance. So we can consider this example of the circuits like that one after 5 tau. Any coils can be replaced by the short circuit. Yeah? So what is in fact the resistances here? Look, the R1 is short circuit by the coil, in fact, so we haven't these resistances, we've got just the short circuit. This coil, it is short circuit, and so we've got just the two resistances which are connected in parallel, giving the 2 ohms. So we can say that we've got the only the 2 ohms resistances connected to the E voltage source. Sorry. And so on. The same story about the energy, which is stored by the inductor. As you know, according to the transient analysis, for the steady state, we've got the maximum current and the zero voltage drop across the coil. So this is not possible. This is not possible to get some or calculating some power on this ideal component. Yeah, because if we have the maximum current, which has some value, the voltage is equal to 0. So the power is equal to 0 also, yeah, because this is the multiplication of the V and I. So we've got the energy stored only connected with the process of release phase, storage phase, and only in that part of time, we can say that some energy can be stored. There is no power dissipating energy on these components also, and the stored energy is given by that format is 1/2 Li maximum squared. So as you see, it depends on the maximum current in powered current, maximum current, and depends on the inductance. Of course, if you've got the higher inductance of the coil, you can say that the higher voltage across it can be induced also, and the higher energy can be stored. What is the stored form of energy? As for the capacitor, it was the electric field, and for inductors, the energy is stored by the magnetic field. Okay, so that's coming back. Okay, guys. So can you hear me?
Yes.
Yes.
So at this moment we stopped the one of the longest presentation. What are you thinking about it? Do you know something more about the coil capacitors? Do you understand it?
Yeah, it's better than
A
previous.
bit.
Sorry.
Kind of.
Yeah. Yeah. Maybe. Yeah. We will see. Yeah. No, I hope that this lecture was so helpful, or will help to you to understand it much more. Okay, you can go to the book which was given the beginning of the course. Yeah, do you download it? Do you download this book?
Yes.
Yes.
Okay, yes, but sometimes when the people says it means that they do it, then they do it, then they don't do it. Okay, so if you wanted to more information about it, I think this book it is right very very good, and please just read it about it if you wanted to know more. Okay, guys. So I think we can stop at this moment. Yeah. But I have a question. What about the classes? What do you think about how we can solve the problem with this with the classes taking into account that form of communication? Yeah, by the Zoom or the, I don't know, Skype.
Maybe
If we would have just some exercises that we could like do practice from the book, maybe.
Yeah, I gave you the book. Yeah, also that's right.
Yes.
There's a lot of examples. However,
it would be best if everyone had a graphics tablet,
But we cannot expect that.
which you can draw. Yeah.
But we cannot expect that. But what
Yeah.
about you give us some exercises to solve, and then we can present it like to you
On Zoom, maybe.
yeah, but
via
you know,
the Zoom.
I see the presentation. How it looked like. I don't know. You wanted to show, for example, I don't know, the piece of paper when the example was solved.
For example, I mean, I'm not sure how the screen share works, but
Yeah, it is possible. But I have another idea. If we had like some exercises, like a list of exercises to do, and then we could just like try to do them, and then we could like remember which ones were like which one we had troubles with, and then like we could like with you go to just them via Zoom or something.
Yeah, but the problem is how I can present you, for example, check it. I'll present you. In fact, present you what is the, for example, good way to solve it. Yeah, you know, because the best way was, for example, like that. I will have, if I will have, for example, the board. Yeah, a whiteboard, for example. Yeah, at home, I haven't it. So that's the problem. Another one, I have the integrated camera on the laptop. So, for example, if piece of paper, yeah, for example, it is very hard to at the same moment talk to you and solving some and showing you how we can solve the example. That's the problem. I know that when I click on the share screen, I can choose the whiteboard. Yeah.
Yeah, but with the mouse, it's not really.
You can make maybe photos of the tasks you made on paper.
Yeah, but then
and
it's not.
show
Then
us
it's not live. So it's a little bit harder to present.
Okay, so maybe.
I mean, there has been a lecture. I mean, some people are doing the lectures, online lectures. Like they come to the university, but the students don't. And then because I know I know it's funny, but I know that happens because I am one of the people who like sets that up. And we have some like tablets and stuff for that.
You know, I know what I mean. Believe me.
I get if you don't want to do this. I wouldn't want to do that either.
Actually, you know, I have a very very small child. I think it is not a good idea to, going to the university at this moment. However, at the dean, I have the information that we have to reduce any contacts between between us to at least to the minimum. In fact, so that's why we have to stay at home.
No.
I mean, you're not muted again.
some
Just
teachers
like meetup,
they doesn't care about it. Yeah, and I go to the university, and of course they can use the board. And for example,
I mean, there's no students, so that's a little bit better. But
this is not the no. In fact, it is not the case that there's no students. The problem is that also the teachers and the scientists are leaving the country and are going to some conference, and they're coming back. So
that
they have some quarantine also. So in fact, believe me, it is it is not a problem with students, but the problem is a general the people which can appear on the university. It doesn't matter that this is students, doesn't matter that is a teacher. The problem stay the same. We don't know what the situation in fact has the personality. Personally, any people would have the situation. We don't know they are ill or not. Of course, I agree with you that with the students, in fact, the students, the young people, it is the problem is that they could be they could have some virus, of course, but they haven't any.
Yeah, I mean, and there's just a lot of students, so there's like a higher chance.
Yeah, that's right. Yeah, so that's the problem also, and we have to reduce this context because also we've got the families, we've got the oldest parents and the rest of the family. So in fact, it is not so easy according to the point of view, for example, the teachers. Yeah, also for me. Yeah. Okay, I think at this moment, please go to the book what was given by me at the first classes. Okay, do you download it also?
Mm-hmm.
No,
so if someone can send it to me, I can put it on the Google Drive or something, unless it's there already.
Okay. Please start to make these examples. Let's starting from the last time I showed you the branch analysis, as I remember, voltage dividers, yeah, current dividers, yeah. However, please starting to make the examples using the nodal analysis. Okay. I will prepare maybe some examples on for example, on the sheets. Maybe I will make the photos and using this share screen, I can show you and tell you some information step by step what we have to do. Maybe that form will be the best at this moment. Of course, the consultations are open at this moment, any time. So if you will done some, if you do some examples, you can send the for example the photos of the solving examples. Of the examples, what was solved by you, and send it by email to me, and then I can check it. Yeah, for example, yeah, it is also some idea. What else? Maybe I don't know. Maybe I will find some extra some external camera at home, and then it will be much more easier to, for example, on the live stream, making the examples on the sheet, and you will be able to observe it. How I will make it. Yeah, and I will talk to you about what we do in the next step. Maybe that form will be the best. But at this moment, please starting the examples using the nodal analysis. Okay. And we will see in the next week, yeah, on the Tuesday, I think, yeah. On the Tuesday I have.
I've lost track of time.
Sorry?
I've lost track of time already, but yes.
But yeah, on Tuesday we have classes, I think.
Yeah, that's right. Yeah.
Yep.
So I don't want it to.
But we have practice on Tuesday, so how would we go about?
Okay, I don't want it to.
That's what we were talking
about. For example, create the meetings for the people's for the first and second group. Yeah, I think we can make these courses for the classes for all of you. Okay.
Yeah, of course.
I think it is the best idea. Okay, as you see, yeah, this is my son was coming here, and you know I was closed in my room, but as you see, the 4 hours is enough. Yeah. Do you wanna do you wanna say something about the electronics, guys? Hey, Krzyś. No. Okay. No. Okay. So I think we can stop at this moment. So I will prepare some example also, and I will send it by emails to anybody. Okay. I will try to find. Krzyś, what are you doing? I will find the external. I will try to find the external camera at home, and maybe it will be work. Krzysiu, it will be work that I will just make it online some examples, yeah, and you will be observed how I made it. Okay.
Okay, thank you. We'll be very grateful.
Yeah, I know the situation is so hard at this moment. So any ideas are good. We don't know what happened. Probably, I think that probably it is not the end of the problems. So the absence on the university can be extended. Yeah, I think so. But let's waiting for the official information. Okay.
Do you know maybe when we can expect official info? Or do you have no idea?
I think in the next week. Why? Because in general, we have to coming back on 25th. Yeah, 25th of March. Yeah, that's right. So I think if the some issue, if the some decision will be held on. Hey, come on, guys. I think in the next week we will know something more about it. Yeah. So we have to just make it. I don't know how you can solve the problem with the laboratory. Yeah, that's the problem. In fact, yeah. Do you speak with the Bogusz Stempak about it?
We've sent him an email about this whole situation, but we haven't received from his back yet, so we don't know currently what's going on.
Yeah. The Bogusz Stempak is called for me in the last week, and we are thinking about what we can do. So as you see, the practice laboratory, in fact, it is the very weak point at this moment. If you have some ideas about the laboratory, how we can solve it, please write the email to the Bogusz Stempak. Okay. Also, maybe some theoretical. I don't know. No, it is not a good idea. Also, no, I don't know at this moment. So maybe Bogusz will create something more.
At least it's better than the laboratory classes.
Sorry?
At least it's easier to solve than the laboratory classes.
Laboratory classes?
Yeah, like maybe. Laboratory, because
maybe
those are not possible remotely.
Yeah. Also, personally, I have a problem with the students which has the embedded systems where we have to programming, and this is also laboratory where we have some boards based on the STM microprocessor. they are on the university, and I haven't got idea how I can help him to create that type of courses by for example, Zoom. Yeah, because I don't know, how I can teach the programming in practice without the boards, without the microprocessors. Yeah, that's the problem. Okay. So sorry for that. Guys, thank you very much. We'll see on Tuesday in the next week. Okay. So we are. Let's stay in touch by email, of course. Please feel free to write to me if you have some problems, if you have some extra idea. So at this moment, please starting to make the examples by nodal using the nodal analysis. Okay. So I think in the end, maybe on the weekend, I will send you some extra examples. Okay. And then I hope so. I will present you using the external camera. Maybe it will be work. Okay, so thank you very much that you wanted to hear about the next lectures. Thank you so much, and see you soon. Okay.
Thank you very much.
Thank you.
Thank you.
Thank you.
Bye.
Bye.
Bye.